so far we have been discussing free field quantization. However, there is nothing much interesting that we can do in free field quantization, like scattering of particles. Two particles come and then interact with each other, they scatter and then go out. So, processes like scattering or absorption of particle, one particle is incident onto some other particle and it is getting absorbed, or decay of a particle of an unstable particle and so on. None of these physical processes you can understand in free field theory. So, almost everything that is interesting is not explained in free field theory. For that you need to introduce interactions. So, what we need to actually study is interacting field theory. So, what we will do is we will introduce interactions in classical field theory in a very simple example, and then we will consider interacting quantum field theories. So, let us first consider how interactions appear in a very natural way in classical field theory. And then we will discuss how we can study interacting quantum field theories. One of the very popular example is interaction of electromagnetic field with a charged scalar field. You already know what's the Lagrangian density for a charged scalar field. It is given by del mu phi dagger del mu phi minus m square phi dagger phi. We will see how interactions come very naturally in this theory. As of now, it is a free field theory. The equation of motion for this field theory is del mu phi plus m square phi equal to 0. It is a linear equation, there is no source, and hence it is a free field theory. We will see how can we introduce interactions in a very natural way in this free field theory. To do that, note that this field theory has actually a U1 invariance, a global U1 invariance. That is, if you consider this transformation phi going to e to the power I q phi, and hence phi dagger going to e to the power minus I q phi, then the Lagrangian density is invariant under such a transformation. Here this parameter q is a constant, it does not depend on space time coordinates. So, one natural question that you might ask is, what will happen when you make this parameter q space time dependent? When you make this to be space time dependent, then you notice that the second term here is invariant under such a transformation. It is very trivial, this is phi dagger here. However, the first term is not invariant under such a transformation. So, let us check that. Del mu phi goes to del mu e to the power I q phi. So, this is e to the power I q del mu phi plus phi times e to the power I q I times del mu phi del mu q. And similarly, del mu phi dagger goes to e to the power minus I q del mu phi dagger minus I e to the power minus I q del mu q e to the phi dagger. So, when you consider this term del mu phi dagger del mu phi, it does not remain invariant because of the presence of the second term, and you get additional terms which depend on del mu q. You can write this term here as e to the power I q del mu phi plus I phi del mu q, and similarly here this is e to the power minus I q del mu phi dagger minus I phi dagger del mu q. And if this term was not there, then you can see that if you multiply these two terms, there will be e to the power I cube here, there is a e to the power minus I q here, and hence this term would be invariant. However, it is this which makes it non-invariant. So, what you need is actually something which is known as a covariant derivative, which I will denote as d mu phi, such that this quantity will transfer like e to the power I q d mu phi under the transformation phi going to e to the power I q of x phi, and its Hermitian conjugate d mu phi dagger will transform e to the power minus I q d mu phi dagger, so that d mu phi dagger d mu phi will remain invariant under this transformation. This is so what is this d mu phi? Of course, with a single phi you cannot have such a covariant derivative. However, if you define d mu phi to be del mu phi plus I q a mu phi, then you can see that if this transformation is supplemented by something a mu going to a mu minus del mu q, then this d mu will transfer according to this. So, just check that. So, you have d mu phi is equal to del mu phi plus I q a mu phi, and this transforms like del mu phi goes to e to the power I q del mu phi plus I del mu q phi, and then this term here transforms like plus I q times a mu goes to a mu minus del mu q, and then this phi goes to e to the power I q phi. So, this is how d mu phi transforms. As you can see, this term here cancels with this term because of this minus sign, all other terms remain same. So, this what you get is e to the power I q times d mu phi. So, this d mu phi transforms covariantly under the transformation phi goes to e to the power I q of x phi and a mu going to a mu minus del mu q. So, instead of taking the Lagrangian density to be del mu phi dagger del mu phi minus m square phi dagger phi, if you take it to be d mu phi dagger d mu phi minus m square phi dagger phi, where d mu is given by del mu plus I q a mu, then this quantity will be invariant under such a transformation. This is known as a gauge, this is known as the gauge transformation. And this a mu is known as the gauge field. The zeroth component of a mu is the scalar potential, and the ith components they constitute the magnetic vector potential. So, this is the electromagnetic field. If you want dynamics for this a mu field also, you can add a kinetic term for the gauge field, which will be given by f mu nu, f mu nu. So, this Lagrangian density involves the gauge field and the complex scalar field. Now, you look at the equation of motion for this field. Okay? You can see that in the Lagrangian, if I expand this Lagrangian, then this will have a kinetic term for the gauge field, and it will have a kinetic term for the complex scalar field, which is del mu phi dagger, del mu phi, and it has the mass term for the complex scalar field, which is m square phi dagger phi, but there are additional terms involving a mu as well as phi. So, what are these additional terms? If you look at this d mu phi dagger, d mu phi, then this is del mu phi dagger minus I q a mu phi dagger and del mu phi plus I q a mu phi. So, this is del mu phi dagger, del mu phi, and minus I q a mu times phi dagger del mu phi minus del mu phi dagger phi, and then plus q square a mu mod phi square. So, the additional term that you will get here is of this form minus I q a mu phi dagger del mu phi minus del mu phi dagger phi, and then q square a mu mod phi square. So, if this term was not there, then you would have got del mu phi plus m square phi equal to 0 for the scalar field equation, and del mu f mu nu equal to 0 for the gauge field equation of motion. But because of the presence of this term, you will get additional terms in these equations of motion. So, you will have additional term here. So, what is the use of these additional terms? For example, if you look at the vector field equation, here you will get something like q times phi star del mu phi minus del mu phi dagger phi, and then you will get I think it is nu q square a nu mod phi square, terms like that you will get. So, this simply means that if this term was not there, then it would have behaved like a free electromagnetic field, but because of the scalar field, because of the presence of scalar field, the dynamics of the gauge field actually changes. So, therefore, these terms are responsible for the interaction of the scalar field with the gauge field. So, these terms are known as the interaction part of the Lagrangian. All right. So, in general, what happens is, when you consider a field theory which involves many fields, you have the free part of the Lagrangian for each of these fields, and then there is an interacting part of the Lagrangian which involves the interaction of various fields. Here you can see all these free parts are quadratic in the fields and their derivatives. This is quadratic in phi dagger phi, this is quadratic in the derivatives of phi, and this term here f mu nu, as you know, is del mu a nu minus del mu a mu. So, this term here is quadratic in del mu a nu. So, all these are quadratic terms, whereas the interacting terms are not quadratic, they are of higher order. Here this is cubic in the field because there is a mu, there is a phi, and there is a derivative of phi. So, this is a cubic term, whereas this is a quartic term, there are 2 a mu's and there are 2 phi's. So, these interaction terms are usually higher order in the fields. Any field theory which have a quadratic term in the fields is basically a free field theory, whereas if you have cubic or higher order term, then those are the terms which introduce interaction in the theory. In fact, you need not have an additional gauge field here. For example, if you consider, let us say, a real scalar field theory with the Lagrangian half del mu phi minus half m square phi square plus lambda over 4 phi fourth, a phi 4 theory like this, then this term will be the interacting term, because the equation of motion for this will be del mu phi plus m square phi square minus this is equal to lambda phi cube. It will look something like that, and as you can see, this is no longer linear in the field phi. So, this term is this is due to the interacting term, and the field is no longer a free field, it is a self-interacting field. The field interacts with itself. So, typically what you will have is, in general, the Lagrangian will have a free part, which I will denote as L0, and it will have an interacting part, which I will denote as L prime. Let us denote as L prime to be the interacting part of the Lagrangian. The question is how to quantize such a theory. Correspondingly, if you consider the Hamiltonian, the total Hamiltonian, then you will have a free part of the Hamiltonian, and then you will have an interacting part of the Hamiltonian, which I will call as H prime. So, our task is to quantize such an interacting theory, to find the spectrum, and then the question that we would like to ask is, suppose you have a state psi of t at some time t in presence of such an interaction, what is the evolution of such a state? Or in other words, suppose at t equal to minus infinity, the system was in a state which I will call as A in, what is the probability of this state evolving to some other state which I will call as B out as t goes to plus infinity. What is the probability amplitude? The probability amplitude is this, and this is what we would like to evaluate. So, let us consider such an Hamiltonian, and then we will see how to proceed and how to quantize such a theory. Before that, I would like to introduce you various pictures in field theory with using which you can quantize. We have, although I have not emphasized so far, what we have been doing in the free field theories until now is we are assuming the observables or the operators to be time dependent. So, we have in the real and complex scalar field, we have seen that this field phi has the time dependence, whereas the states are time independent. You consider vacuum state and then you consider a dagger k, creation operators acting on the vacuum, and then you get the entire spectrum this way. So, these are time independent, whereas the operators or observables are time dependent. This is known as the Heisenberg picture. So, in the Heisenberg picture, the operators are time dependent, the states are time independent, and the time evolution of the operators are in fact governed by the Heisenberg equation of motion, which basically says that if A of t is an operator, then dA over dt is minus I commutator of A of t and the Hamiltonian. You can also consider the operators to be time independent and the state vectors to be time dependent, and this is what is known as the Schrodinger picture. So, in this Schrodinger picture, the states are time dependent, whereas the operators are time independent. Time evolution of the states are governed by the Schrodinger equation, which is so suppose psi of t is a state vector, then h psi equal to I d psi over dt, and hence you can get psi of t equal to e to the power minus I h t psi of 0. You can relate the operators in the Heisenberg picture with the operators in Schrodinger picture by this relation. You can consider A t this will be equal to e to the power I h t a 0 e to the power minus I s t. So, you can either work in the Schrodinger picture by considering the states to be time dependent and the operators to be time independent, and the time evolution of the state vectors are generated by the Hamiltonian, and this is how the time evolution of the state vector is. Or you can consider the operators to be time dependent and the state vectors to be time independent, and this is how the time evolution of the operators is given. In presence of interaction, it is neither the Heisenberg picture nor the Schrodinger picture is convenient to work with. There is something which is called as the interaction picture. And it is quite convenient to work in the interaction picture when there are interacting terms. In fact, we will throughout our lectures we will work only in the interacting picture. In the interacting picture, what happens is you have the full Hamiltonian, which I will call as H0, which is the free part of the Hamiltonian, which involves only the kinetic terms and the mass terms of the fields involved, and then the rest all of the terms in the Hamiltonian, which I will call as the interacting part of the Hamiltonian, and I will denote it as H prime. What happens in the interacting picture is that in the interacting picture both the states as well as the operators are time dependent. However, the time dependence of the operators in the interaction picture is governed by the free Hamiltonian H0, okay? Whereas the state vectors are also time dependent, but the time evolution of the state vectors is determined by the interacting part of the Hamiltonian. So, how is that consistent? We can, let us say you are in the Schrodinger picture, you know what is the Schrodinger equation of motion, it is the full Hamiltonian H acting on psi equal to I d psi over dt. What we can do is, we can first introduce the operators in the interacting picture by saying that is the operators in the interacting picture is e to the power I h0 t e to the power minus I h0 t, and I will introduce the state vectors in the interacting picture as psi t, which is e to the power I h0 t psi t. This is just a definition. So, you start with this definition for the state vectors, and you use the fact that psi t in fact is the state vector in the Schrodinger picture, and hence psi t obeys the Schrodinger equation of motion with the full Hamiltonian. Okay? So, when you do that, let us now see what do we get for d psi I of t over dt. So, you consider I d over dt acting on psi t I. According to the definition of psi I, this is I d over dt e to the power I s 0 t right, and now you can see this is nothing but I times I s 0 e to the power I s 0 t because here h 0 is the free Hamiltonian. In the Schrodinger picture, it does not depend on time. So, therefore, you have this, and then you have an additional term which is given by e to the power I h 0 t d psi t over dt. Okay. So, I can multiply this I here, and I can pull out e to the power I h 0 t outside, then what I will get is e to the power I s 0 t times minus h 0 acting on psi t plus I d over dt acting on psi t. Now, again I can use the fact that psi t obeys the Schrodinger equation of motion in the Schrodinger picture. So, I d over dt acting on psi gives me h psi, where h is the full Hamiltonian. So, this is e to the power I s 0 t times minus h 0 plus minus h 0 acting on psi t plus the full Hamiltonian h acting on psi t. So, this is nothing but, so this implies I d over dt acting on psi t in the interaction picture is e to the power I s 0 t h minus h 0 acting on psi t. But h minus h 0 is h prime. So, this is nothing but e to the power I h 0 t and then h prime acting on psi of t. So, we are not yet done. So, what we have shown is I d over dt psi t in the interaction picture is given by e to the power I h 0 t h prime acting on psi t. Here I will introduce an identity operator which is basically e to the power minus I s 0 t times e to the power I s 0 t. So, if I do that, then what I have is e to the power I s 0 t h prime e to the power minus I s 0 t and then e to the power I s 0 t acting on psi t. This is nothing but, according to our definition, this is psi t t in the interaction picture, whereas this is the operator s prime of t, which I will call s prime I of t, because according to our definition, the time dependence of an operator, any arbitrary operator you consider a t, the time dependence is governed by the free Hamiltonian. So, this is e to the power I s 0 t and then a e to the power minus I s 0 t. So, I will denote this to be the interacting Hamiltonian in the interaction picture. Therefore, if I use this definition that the state vectors in the interaction picture are defined like this, then these state vectors obey an equation where the time evolution of the state vectors are actually governed by the interacting part of the Hamiltonian h I prime of t acting on psi t, where this interacting part of the Hamiltonian is in the interaction picture. So, state vectors, the evolution of state vectors is given by this equation, whereas the evolution of time evolution of operators is given by e to the power I s 0 t a in the Schrodinger picture. So, I will call it as a 0 e to the power minus I s t. Therefore, this a of t obeys a Heisenberg equation of motion as if the Hamiltonian is the free Hamiltonian. So, dA over dt is minus I commutator of a and h 0, where h 0 is the free Hamiltonian. So, we will use this interaction picture and then we will consider the quantization of interacting field theory. So, as usual we will consider the fundamental commutation relation and then we will see what is the spectrum, whether we can find the spectrum or not, or how to proceed and all those things we will see. So, let us consider the commutation relations. You have the Lagrangian which have a free term and which have an interacting term. So, let us say you have the field phi, you can ask the question what is the corresponding conjugate momentum phi of t. Let us first assume that phi of t, they are all in the Heisenberg picture. And then phi x t. So, you again would like to have a commutation relation in the Schrodinger picture, which is I delta x minus x prime. However, as I stated, we would like to work in the interaction picture. So, we would like to consider these operators in the interaction picture. The question is whether the same commutation relation holds in the interaction picture. In general, it will not hold. However, we can make an assumption that this interacting part of the Lagrangian does not contain any time derivative of the field. So, what we will assume is del 0 phi, this interacting part does not depend on del 0 phi Li on. So, this commutation relation of course will be same as the commutation relation in the free field theory. So, this will hold. Now, you can introduce the operators in the interaction picture. We already know what are the operators in the interaction picture. In the interaction picture, AI, if I call as an operator A in the interaction picture, this is e to the power I s0 t A0 e to the power minus I s0 t. What we are interested is how the operators in the interaction picture are related to the operators in the Heisenberg picture, not the operators in the Schrodinger picture. Of course, it is trivial to determine because we know the operators in the Heisenberg picture are related to the operators in the Schrodinger picture by the relation e to the power I s t A of 0 e to the power minus I s t, where s is the full Hamiltonian, right. So, you can invert this relation. This will tell you A0 is e to the power minus I s t A t e to the power I s t, and you can substitute it here. When you substitute this here, what you will get is e to the power I s0 t e to the power minus I s t and then e to the power minus I s0 t e to the power I s t. So, thank you. E to the power I s t will come first with a plus sign and then e to the power minus I s0 t. You can denote this to be, you can define an operator u. So, let us introduce. So, let us introduce this operator u of t to be e to the power I s0 t e to the power minus I s t, then A I t equal to u A t u inverse, right. This is what we get. So, therefore, now you can see that if you consider this commutation relation phi x t pi phi of x prime t, the fundamental equal time commutation relation, this is I delta x minus x prime. This is the commutation relation in the Heisenberg picture. Then you can operate u inverse on both sides. So, u phi x t pi phi x prime t u inverse, this is again going to be I delta x minus x prime, whereas this will give you the operators in the interaction picture. So, this is basically going to become phi I, where phi I is the operator in the interaction picture. Similarly, here pi phi I in the interaction picture. So, the commutation relations in the interaction picture also holds, the same commutation relation holds for the interaction picture. So, as far as the commutation relation is concerned, we are perfectly fine, but then the next question is how to how can we write the general solution, what are the creation and annihilation operators, and so on. In the free field case, at least we already knew that this field phi admits plane wave solutions which are e to the power minus I k dot x. So, the most general solution you can write as phi equal to integral dq k over 2 pi cube to omega, then a k e to the power minus I k dot x plus a dagger k e to the power I k dot x, and you can put it in the fundamental commutation relation. You can find what is the commutation relation between a and a daggers, and then you know how to interpret this a, these a's to be these a's as the annihilation operators and the a daggers as creation operators. However, in presence of interactions, we do not have the luxury to do this, because we cannot in general construct a solution like the most general solution in this form. So, we have to worry about how to proceed and then quantize an interacting field theory. So, we will discuss more on this in the next few lectures. All right.